That's where we stopped last time. So we proved that given a set vector space V, the span of S space, just to remind you, the span of a set of vectors S is given by the set containing all linear combinations of vectors in S. Now, clearly, everything happens inside the vector space V, right, where S belongs as a set. But something that I don't know if I mentioned last time, the set S itself has to be a subset of its span. Do you see why that is the case? Like, how can you see a vector in S as an element of its span? It's not working. Okay, so if you take a vector, let's say x, so let x be a vector in the set S. How can you see x as an element of the span of S? Pretty straightforward. You can write x as a linear combination of the vectors in S in the following way. Itself times the scalar 1. You can add, if you want, other vectors with the scalars 0 multiplied by, if you really want to, but it doesn't matter. So written like this, it becomes an element of the span of S. All right, so S, this S here could be a finite set. However, its span becomes an infinite set in V. And we actually proved last time that the span of any subset S is a subspace of V. Okay. So one more part left to this proof. And that is the second one. Any subspace of V that contains S must also contain the span of S. So let's say W be a subspace of V such that it contains S. We want to show that it must contain the span of S as well. So I'm concentrating on the thing that I need to show. Again, I want to show that the set is a subset of another. So I'm going to start with an element of the set on the left and prove that it belongs to the set on the right. So let Z be a vector of the span of S. I want to show that it belongs to W. But because it is in the span of S, you can write Z as a linear combination of some vectors of S. Let's say A1, U1 plus A2, U2 plus AN, UN. for some vectors u1, u2, or un in S, and some scalars in the field. All right, so the question now is, why does that sum belong to W? So let's see, what do we know about W? We know that it is a subspace, right? So it's closed under addition, scalar multiplication, whatever you want. It's closed. And more than that, we know that it contains any vector that S has, right? It contains the entire set S. So then, look at the vectors u1 through un that show up in the sum here of Z. Since they belong to S, they will automatically belong to okay. So what is Z in the end? Written like this is going to be a linear combination of vectors in S, but I can see it as a linear combination of vectors in W, because every vector of S is also in W. All right, but we said that W is a subspace, right? So subspace is closed under addition, is closed under scalar multiplication, so it's closed under any linear combination you take, right? You're still in the subspace. So the Z has to be in W, again, because W is a subspace. Okay? So again, that means if you have a set of vectors S, part of a subspace W, it can never be the case that the span is on the other side here. Okay? The span of S will always sit in between S and any subspace that contains S. So it will always be the case that I have something like this, right? No matter what W I consider. Okay. So we're going to look at a special case now, and that is the case when the span of a set of vectors gives you the entire vector space V. Okay, so I have a set S such that its span is the entire vector space. Then I'm going to say that S generates V. Okay, so I'll say that S generates V if the span of the set of the vectors in S will give you V. So what does that mean? Start with R. Can you give me a set of vectors that generate R2? Such that when you take the span of that set, you generate R2.
1, 0, 0,
1, 0, and 0, 1. Good. But what you gave me here is more than a generator, right? You actually gave me the best thing possible, which will be a basis, and that's something that will be section. However, if to these vectors, these two vectors, I add a third one, many as I want, as long as it's different. Generating, right? Let's see why. Well, I want to show that two sets, this one and that one, are equal. Show that two sets are equal. Double inclusion. So I need the set on the left to be a subset of the set on the right. I'm going to put a check mark next to it, right? Because everything happens inside R2. I'm not getting outside that space. So let's see backwards. If I take a vector in R2, which looks like this, can I write it as a linear combination of vectors in S? Yeah, and I don't need all of them. I can just make use of the first two. So X is A times the first. So it becomes an element of the span of S. Okay. So double inclusion, it holds. All right. V equals matrices 2 by 2 over a field F. This is a vector space over F. So let's see. Like this. Yeah. 1, 0, 0, 1. The other diagonal. Like this. Yeah. Well, let's think about it. Does it work? No. Why not? Well, to answer this kind of question, let's say, tell me how you would generate this. Just no way, because from that set S that you gave me, all I can generate is something like this. Correct? Which is a matrix that looks like this. And that's definitely not all the possibilities, right, in matrices 2 by 2. Okay, so we need another set. That is generating, of course. So the problem with the previous was what? That you were generating diagonal at the same time, but, right? Yeah. No, you want to generate every entry separately, right? So how do you do that?
1, 0, 0, 0.
I'm just allowing a single entry at a time. And again, this is going to be the best possible choice in the sense that, again, it will represent the basis. But I'm allowed at this level to just add, more matrices into that set that I'm not going to use a generating set. So it's going to be a generating set since an arbitrary matrix A, B, C, D 2 by 2 over F is just A times the first matrix plus B times the second plus C times the third and plus D times the last matrix. So let me add this here. If I take this S and I take the union with any matrices you want, right? So just add a bunch of matrices in there, would still be generating. Okay, but let's not just get, we'll see more of this in the next section with the basis. There are still a couple of things that I want to say about the span of a set of vectors before we move on. So far, again, we've seen this, that the span of a set of vectors will always contain the set, right? That's one thing. Then we've seen this idea that there is nothing in between a subspace and its span. There is no additional, there is nothing in between set and its span, no other subspace. Okay. So now let me say note. A couple other things that we're going to need about span. If, let's say, A is a set of vectors and B is a set of vectors in the same vector set, vector space V. And the same holds, well, the same as what? If A is a subset of B, both sets of vectors in V, then the span of A is a subset of span of B. Okay, let's see why that holds. So I'm still trying to show that a set is a subset, which means start with an element of the set on the left. So Z, an element of the first set, span A. I want to show that Z is in the span of B. Okay, so what does Z look like? Well, it's going to be a linear combination of some vectors of A. With some coefficients in the field. So why is Z then in the span of B as well? So what does it mean to be in the span of B? It means it should be a linear combination, right, of vectors in B. It is a linear combination of vectors in A. However, subset of B. So all those elements here, U1 through UN, being elements of A, they are in particular elements of B. So I can see Z as being a linear combination of vectors in B, therefore it belongs to the span of B. Okay, so kind of whatever you have between A and B is preserved at the level of their spans. 2. We said before that every set of vector is a subset of its span. The subset could also be equal, right? Is subset equal? The question is, when do we have equality? When what? So when is S equal to its span? All right, so let's think about S a little bit. What can it be? Can it just be a bunch of vectors, like 2, 3 vectors there? S itself? If S would have 2, 3 vectors, how many vectors would its span have? Infinitely many, right? The span is a set containing all the possible linear combinations, right? So if S contains a finite number of vectors, its span can never, I mean, it's going to be infinite, so they can never be equal to each other, right? So S has to be large in order for this thing to make sense. Okay, now what do we know about the span of S? We know that it is always a subspace, right? We proved that the span of any set of vectors is a subspace. So in order for this to make any sense, S itself would need to be a subspace, right? To equal its span. Well, it turns out that it is an if and only if kind of condition. So in general, we have that a set equals its span if and only if S is a subspace of V. So let's prove this last statement now. Okay, so it is an if and only if kind of statement, so I have to go in both directions. One of them will be very easy, and it's this one. Why is it so easy? So I'm assuming the statement on the left is a subspace automatically, so I'm assuming that S equals its span. But we already proved that the span of any set of vectors is a subspace of V. Then S has to be a subspace of V. Okay. Well, let's see it backwards. So now I'm going to assume the statement on the right, that is S is a subspace of V. And I want to show that it equals span. Okay, again, I need to show that two sets are equal, double inclusion. One of the inclusion, a set is always a subset of its span. We've already seen that. So all we need to show now is that the span is a subset of S itself. So I'm going to start with an element Z in the span. And I want to show that it belongs to S. So being in the span, it must look like this, a linear combination of vectors in S. So I'm taking a linear combination of vectors. I want to show that the resulting thing is in S. Why? Right, so I have an additional assumption here, right? S is a subspace, so it's closed under addition, scalar multiplication, right? So it's closed under linear combinations. Okay. So that's pretty much all I need, like statements that we're going to use about sets and their spans. Okay, so we know that S is always a subset of its span. They are equal if and only if S is a subspace itself, and whatever relation I have between two sets A and B holds for their spans, right? The inclusion-wise, I mean. Okay, so I'm going to move on. To section 1.5. It's called linear dependence and linear independence. So we're going to start by looking at the sentence. So you have a set of vectors, S, a set of vectors in a vector space V. Then we're saying that the set is linearly dependent if there is a linear combination of vectors in the set S that will give you the zero vector. But you know how you can always get the zero vector with all zero scalars, right? That's trivial. So they're adding here that not all those coefficients can be zero at the same time, right? Otherwise, it's trivial. So a set is dependent if there is a way to find a linear combination of vectors in the set that will give you the zero vector. If you cannot find such a linear combination, then the set will be called independent, if such a thing doesn't exist. Okay. Let's say, is the following set linearly independent or linearly dependent? So I need to look inside a vector space V. I'll go to matrices, let's say, first. I think I should stop. Yeah. You're given a set of vectors. In this case, the vectors are matrices inside a vector space, and you're asked to figure out if the set is dependent or independent. Now, how do I answer such a question? Well, being dependent or independent depends on that existence of a linear combination of vectors in the set that will give you the zero vector. So you need to kind of look at a possible linear combination equal to zero and see what happens. So is it possible that a scalar times this matrix, first matrix, plus a scalar time matrix plus a scalar times the third matrix, and plus 1 times the last matrix. Will give you the zero vector. What's the zero vector in my vector space? 0, 2 by 2, right? So zero matrix. If the answer is yes, with not all coefficients 0, then my set will be dependent. If the answer is no, I need to have all coefficients equal to 0, then my set is independent. So basically, the answer is in solving this kind of equation. Now, sometimes the vectors are pretty nice and you can just notice some kind of connection between them. Like, for example, if one of those matrices would be a scalar times another one, you would be done. Make sense? Because you would make the combination one of them minus that scalar times the other one equals 0 and you're done, right? It's not that simple here, right? It's not visible, at least. So what do you do then? Well, you just go ahead and try to solve that. So what does it mean? 2a plus b equals 0 plus 2c plus 2c Let's transfer everything in terms of a. B is negative a. Yeah. Let's say a equals -1, b is -1. So there is a one of those is equal to the 0 matrix. It has a non-zero solution. Dependent. By convention, the set is linearly independent. A way to find the linear action of vectors in that set with non-zero coefficients, because there are no vectors in that set. Right? Great. How is this set? Dependent or independent? Didn't hear you. Yeah.
I think independent.
Set amount of some vector, right? So, and I get the zero vector. So vectors from my set equal to the 0 vector. Therefore, my set is independent. Okay, what if I have a single vector in my, so that would mean the set is linearly independent, because the only way to form a linear combination to equal 0 is with 0 scalars. Okay. What if I have two vectors in my, when would this set be dependent? When would it be independent?
With the multiple of other.
Dependent, okay. Is linearly dependent if I would have a linear combination of the two equal to 0, so AU plus BV equals 0, but then, right, so U would have to equal a multiple of the other. Otherwise, if this doesn't happen, independent. Okay. Now, so we know one vector, we know two vectors, but from three vectors on, I get into a situation like example 1 there, right? When I don't know exactly what's going on. If things, like if I don't figure out. So now, here are some ideas that can be helpful. So here's what we're going to prove next. If I have a large set of vectors, like 3 or more, 100 vectors, but inside that set, I notice a subset that is dependent, how will the big set be? Set is a multiple of the other, of another one, right? So I notice a subset of two vectors in there that is dependent. Then the entire big set will be dependent because I can come up with that linear combination that defines dependency with 0 coefficients for things that I noticed, right? So if I have a dependent subset of a set, then the entire set has to be dependent. Like if I have this big set, would that tell me that the big set is independent? No way, because something can happen outside that little set. However, it goes backwards now. If I have a big set that is independent, I pick a subset. That subset will have to be independent. Make sense? Okay, so that's the thing that we're going to prove next. Two things that we'll prove next. Here, no. Okay, so first result. If S1 is a subset of S2, with the smaller one being dependent, then the big one has to be linearly dependent as well. And the proof is pretty straightforward. As we said, you can use 0 coefficients for everything else. The small set is linearly dependent. then there exists some linear combination of vectors in S1 that will give you the. So there exists V1, V2 through set as S1, and there A1, A2, AN, such that V2 plus AN, VN gives you the zero vector, and those coefficients cannot be all zero at the same time. Of vectors in S1. Vectors in S1 are also vectors of S2, right? Because S1 was part of S2. So I can see this of S2. In S2, there exists a linear combination of vectors that gives you the zero vector with not all coefficients equal to zero. Linearly dependent too. Corollary. The opposite thing that I mentioned before, if a small, right, if you're looking inside a set that is independent, what you see in there has to be independent as well. If the independent, linearly independent as well. Proof. I can kind of go with the same proof as above, but since it's mentioned to be a corollary, it should be somehow a consequence of the theorem above, and it could easily be seen as a consequence if you go with the proof by contradiction. So if I'm going to assume to the contrary, so that S linearly dependent. So which is the smaller set, right, is dependent. The theorem above, what does it say? The small set is dependent, and the big set is. Yes. Using the big set has to be linearly dependent. That's one assumption that we have, which is that the big set is independent. But everything writes its own thing, so this means that it's a contradiction. So the proof is a contradiction. Okay. Move on. So again, the question was, what do I do about bigger sets of vectors? How do I decide whether they are dependent or not? So now we kind of know to look inside those sets for smaller dependent subsets. Now, here's the question that we have next. I have a linearly independent set of vectors, this set S here. And I'm trying to extend that set. What does that mean? I'm trying to I'm trying to add vectors to that set. Now, why would I want to do that? Because of what will happen next, which is that idea of a basis that I already mentioned before. So it turns out that in order to get the basis of a vector space, it's always enough to start with an independent set and expand it as much as possible, or start with a generating set and shrink it to a basis. Okay? So we're heading in that direction now. I have a linearly independent set of vectors, and I'm wondering what happens if I add an additional vector to it. And here's exactly what happens. If the vector that I'm adding to my set is in the span of the original set, then that creates a set that is a new set, right? The larger set would become dependent. And it turns out that if and only if kind of thing, right? So an independent set such that the set remains independent, I better add something that is not in the span of the original. Pretty much this. Okay. Set. And I want to show that if that is the case, then V has to be a vector in the span of the original set. Okay, so we have an assumption that S union. So what does that mean? Well, it means that there is a linear combination of vectors in that union that will give me the zero vector, right? With not all coefficients equal to 0. So here's how there exists n vectors, some n vectors, right, in that S union V, such that A1U1 plus A2 AN will give me the zero vector for some coefficients not all 0 at the same time. Okay, so now I haven't named the vectors in S or anything, so those U that additional vector V. Now my question is, do I have to use that additional vector V, or could my U1 through UN be elements of S? What do we know about S? It's independent. Okay. So being independent means that there is no way to form a linear combination with all non-zero coefficients, right? Vectors in S only. So I need to use V, right, in order for this thing to make sense. So one of those vectors, U1 through U, no loss of generality, is that vector V. One of them has to be V. Let me assume that U1 is V. We said that I have to use V, so the coefficient cannot be 0, right? The coefficient of V cannot be the 0 coefficient. If U1 is V, then I have A1V as my first term in the sum, and then everything else I'll Now, why am I doing this? Remember what I'm trying to prove? I'm trying to show that V is an element of the span, right, of S. So V should be a linear combination of vectors in S. Here is that F is a field, so every non-zero element in a field has an inverse with respect to multiplication. Here is that inverse to the other side, kind of like dividing by it if they were real numbers. And then I'll just distribute. So now the vectors that I'm using on the right here, they all have to be elements of S because, right, U1 through UN were in S union V. I already used V, so everything else will have to be in S. So what I wrote here is a linear combination of vectors. And I'm done, right? That's what I needed, that V is an, I need to show that V belongs to the span of S. Okay, let's go backwards. So now I'm assuming that V is an element of the span of S. But S union V is a linearly dependent set. Okay. So what does it mean that V is in the span? It means again that it can be written as a linear combination of some vectors in S. Let me use maybe different letters. Okay. So what I'm trying to show is that S union V is linearly dependent, which means there should exist a linear combination of vectors in that bigger set that will give me the zero vector. Do you see that linear combination? Oh, it's right here. If you move everything to one side, clearly not all the coefficients could be zero because I have a -1 coefficient at least, so they cannot all be zero. S union this vector has to be linearly dependent. Any questions? All right. So that takes us to basis. Okay, so in order to have a basis of a vector space, I need a set of vectors at the same time independent and generating. Okay, so they both need to happen at the same time. So for example, we've already seen a basis for this vector space, right? Matrices 2 by 2 over F. The basis will be given by that set that you found when you were asked for generating only, right? But I was telling you back then that for generating, I can add more vectors, right? But to be a basis, that's it. I have to stop here. So this set is generating, and hopefully it's clear. Why is it independent? Okay, right? If I were to form a linear combination with those four matrices, what would happen? If A would be, let's say, then A will up in position 1, 1 in that matrix, right? If B would be the scalar for the second, it will show up in position. Show by itself in one of those four positions. So to get the zero matrix, you should get all the scalar equal to 0. So it is also independent in generating, therefore it is a basis. For me. Impact in what would represent So what was the problem with 2 by 2? We wanted to get every entry by itself, right? So how can we get every entry of an M by N matrix? Well, I can use a matrix with a 1 in position ij and 0 everywhere else for every possible I and j, right? I between 1 and m, j between I and 1 and n, right? So I get an M by N matrix which has a name, it's standard. So this will be called the standard basis of matrices M by N. So an M by N matrix with 1 in position ij, so row I, column j. Maybe that's not a nice matrix here, what I wrote, so let me rewrite it. So Eij is the matrix with the property that its ij entry is 1, and all other entries are 0. So I take this matrix Eij, and I do this for every I between 1 and m, and for every j. Do I get in the basis? How many matrices? M times n, right? So hopefully it's clear that beta becomes a basis. Generating it is, because it has, with that 1 in each position, I'm going to generate every entry of my m by n matrix. And independent, exactly the same as the one above, because if I take a linear combination, then the coefficients will show by themselves in each entry, ij entry of the matrix. So they will have to be 0, all of them. Okay, so this will be called the standard basis of matrices m by n. There is also a notion of standard basis in Fn as a vector field over F. So how do I generate every vector in Fn? After all, because it's the same idea. Or even R2 or R3 to start with.
Maybe something like the X and Y axis, 1, 0, 0, 1.
Correct. So if it would be R2, you would generate with 1, 0, and 0, 1. In R3, you would generate with... Correct. So in Fn, you would generate with that n, with all position I, let's say, and 0 everywhere else. Those n tuples have names, E1, E2, and they are the standards of Fn. So E sub I is that n tuple with 1 in position I and 0 everywhere else. Okay, so in Fn, I have a set containing n vectors. They are clearly generating, because if I just take an arbitrary n tuple with entries A1, A2, A3, and split it into A1, A2. Make sense? So if I take something like this, and I can split it into A1 times 1, 0, 0, 0, so E1, plus A2 times 0, 1, and so on. Okay, so this set is generating for Fn. It is also independent, because if I take a linear combination of those E sub i's, then the coefficients in the linear combination will just show in that, the corresponding non-zero positions of E. and they will all have to be 0. Okay. Polynomials of degree at most n over a field. So beta should be a set of vectors, but vectors, by vectors, what do I mean? The vectors now are polynomials, right, of degree at most n. So you need to collect polynomials of degree at most n that would generate everything, and they would be independent. Correct. You don't have to think too far away. I mean, it's just 1 up to x to the n. They clearly generate everything, right, of degree, but at most n has to be a linear combination of those. So generate is y. Right? So if I were to have a linear combination of some of those things equal to the 0 vector, which 0 vector for us is the 0 polynomial now. It would have to look like this, right? But the polynomial equal to 0 is only possible when all the coefficients, right, are 0. So this will be called the standard basis for Pn of f, and it extends to polynomials of any degree. So P of f, the set of all polynomials in any degree, will have a basis. It looks like this, but it just doesn't end. Right? It's going to be an infinite basis since I'm allowing my degrees to be anything. Okay, let me see if I have some more examples here. If not, we'll definitely go into the theory, but just to start it now. Okay, let's just look at one more example. So all those vector spaces were more or less famous vector spaces, right? Something that we've seen a lot of. So what if there is something else, right? Something that doesn't fit into one of those nice pictures. So for example, how would I find the basis for the following vector space. And of all 5 tuples with this property. Now let's clarify one thing. Why is this a vector space, first of all, right? Because a vector space is supposed to have, to satisfy a bunch of properties, a lot of properties, right? And what I wrote here is just a set of vectors in F5, right? So it's a subset of F5. If it turns out to be a vector space, it better be a subspace of F5, right? Because that's what the subspace itself. So let's just check that. So to check that something is a subspace, you need 3 things, right? The 0 vector should be in there. Yes, because the 0 vector has the property that its first entry minus the third and minus the fourth gives you 0 because all the entries are 0. Okay. V should be closed under. So what does that mean? If X and Y are 2 5 tuples that satisfy this property that defines V, I want to show that X plus Y has the same. Let's see how this works. Tuples. So X plus Y looks like this. So what does it mean that X plus Y should be an element of V? I need to check that property, right? That it is a vector X plus Y. So that means take the first entry, and that first entry is a 1. Subtract from the third entry and the fourth entry, and hopefully get 0, right? And that clearly holds because I have these properties about the A's and about the B's, because X and Y were both 5 tuples in V. Okay. So V is closed under addition, and finally, scalar multiplication. Why is that? Because if A1 minus A3 minus A4 equals, multiply everything by a C, this will also equal 0, right? Okay, so we haven't done much. We just that this V is a vector space in itself. So how? Now, it's not just to have a where to elements in the base. 5, we said, right? The standard basis. Now, some of those would have to go away, correct? Because V is not the entire thing. Now, which of them would you kick out now? A2 and A5. So you would generate V then with what vectors? With E1, E2, no, E1, E3, and E4. But are those vectors even in V?
No.
So don't I need, to have a basis for a space, don't I need, they need to be in the space, right? So there is no way to, for that, right? This mark, because the class is over. So we'll leave it with this question until next time. Okay? And there will be a while until next time, by the way. So you'll be living with this uncertainty for a while, because on Monday there are no classes, right? Labor Day. So we'll meet again on Wednesday. I'll put some homework in for Wednesday on campus.